Hello, everyone. Before we start this lesson, we're going to go back and review a question from a long time ago in the homework. And had we been in class, right, we definitely would have taken this up when we hit this question. But we'll talk about briefly here. So this is page 32, number 18. It asks you to calculate the final amount of $1 invested at 100% interest for 1 year at different compounding periods. So before I start revealing, this is going to be the express version of that question. Okay, right, the formula, this is going back to grade 11 for compound interest, is P 1 plus I to the power of N. Okay, where N is the number of compounding periods, and P is your principal. Okay, so what this is going to turn into, principal is 1, so it's going to be 1 times that bracket, 1 plus, okay, it says 100% interest, so that would be 1 divided by the number of compounding periods. Okay, and we're only doing this for 1 year, so basically this value down here and this value up here are going to be the same. Okay, so like if I'm doing, say, monthly, then I'm going to divide my interest rate by 12, and I'm going to have 12 compounds, so I have the same number in both spots. So when you start working this through, okay, if you do it annually, so if you earn 100%, and deposit it just at the end of the year, you go from $1 to $2. Okay, no big deal, but that should make sense what's happening there. Okay, for say quarterly, so 4 times a year, okay, you make a little bit more money, $2.44. Okay, and maybe you remember that from the grade 11 course, right? If you compound more often, you make more money. Not a huge amount, but you do make more money. Okay, monthly, it goes up to $2.61 every day. Okay, if you run this through for every day, you get about $2.71. Okay, if you go to every second, okay, which we're not talking an order of millions of compounding periods at a very tiny interest rate, it rounds off to 2.72. Okay, and you really can't get any better than this. If I started going to every millisecond or nanosecond or something, it would still round off to 2.72, maybe 2.73. Okay, like it doesn't really get much better than that. Okay, so what is it saying? There's a limit, right? There's a limit on how much interest you can make. We know it goes up when you increase the compounding periods, but it doesn't go up forever, right? There's a point at which you've squeezed out all the interest you can. Okay, so this next slide basically talks about the same thing, right? That the limit looks something like this. The limit as n goes to infinity of 1 plus 1 over n to the power n. Okay, and the limit as you go through this to 5 decimal places is 2.71828 and so on. Okay, so I guess what I just said there, it never gets to 2.73, right? It maxes out at 2.72 for money there. Okay, so this limit, okay, is so important. Okay, it's called the fundamental limit of calculus. Okay, the limit as x goes to infinity of 1 plus 1 over x to the x is equal to e. Okay, which is that 2.71828 and so on. Okay, now on your calculator, okay, I think it goes 1828 again. Right, you probably have a button that looks something like this, e to the x or e to the n. So if you want to see e on your calculator as far as it can go, you'd want to do e to the power of 1, and that would give you your value for e. Okay, the calculator I have on the computer here, it's just has e plain there. Okay, because you might be tempted to think at first it repeats, right? Because it goes 7, 1828, 1828. Ooh, we got a nice pattern there. But after that, no, it does not have a pattern. Okay, so e is an irrational number, just like pi. Okay, it's non-repeating, it's non-terminating. Okay, it's an important number, but yeah, it's irrational like pi is. Okay, so related to that is what's called a natural logarithm. Okay, ln of x. Okay, so similarly, right on your calculator, right, you have a log button, but you also have a ln button. So that's all that is. Okay, ln of x, and I'll highlight it down here. Ln of x is the same thing. Whoops, sorry, that's not the base. is the same thing as log base e of x. Okay, just like the log button on your calculator is really log base 10 of x. Okay, but yeah, it's related to e. Okay, and it's significant, so it gets its own key on the calculator. Okay, and it's called the natural logarithm. Okay, all the laws of logarithms also apply to ln, right? It's just a different symbol, but it's still a logarithm. Okay, so things like if you had, what's ln of 2 plus ln of 3, well, that means I can multiply those together. That's the same as ln of 6. Okay, all those kind of things still work with ln because it's really just another logarithm. Okay, so for first example, I'd invite you to pull out your calculator here and just follow along to make sure you can get it to work. Okay, but we're just going to go through some computational type stuff here. So here's the first three. Okay, I've got e to the 3, e to the negative 2, e to the power of pi. Okay, so on this calculator, right, I actually have to do a separate step, but you probably just have to press your e to the power button. Let's say e to the power of 3. Okay, hopefully you got a little over 20 there. Okay, if I do e to the power of negative 2, okay, 0.135 and so on, e to the power of pi, okay, is a little over 23. Okay, so it looks like this. Okay, again, I invite you to take a minute, just pump those through your calculator and see what you get. Okay, so the first one is ln of 2. Okay, on my calculator, I have to press ln second. Okay, but there's ln of 2, 0.6931. Okay, and if I do 14, so 14 ln, I get 2.6391. Okay, finally ln of e, so e ln, well, I get 1. Okay, right, because it is base e. What power do I have to raise e to get e? It's 1. Okay, so again, make sure you figure out on your calculator how these buttons work so you're able to run these through. Okay, so we'll talk briefly about how to solve an equation involving e. Okay, it's basically the same thing as how you solve with log, right? Right, e to the power of something is 35. Well, obviously I don't know what power that's going to be. There's no easy way to go from this irrational number to 35. So normally we take log of both sides, but because we're talking about e, we're just going to take ln of both sides. So I'm going to do, what is ln e to the 2x and ln of 35. Okay, the power rule allows me to pull out the 2x. So 2x times ln of e equals ln of 35. Now, one of the nice things about this is because I've used ln, we just saw on the last slide, ln of e is actually equal to 1. So this just becomes 2 to the x equals ln of 35. So that means x equals ln 35 divided by 2, okay, and that is my exact answer. Okay. Again, right, you can run it through your calculator and get an approximation if you would like. Okay, I got 1.7776 okay, on my calculator. Okay. So our last example is going to be about how to convert. Okay. For reasons that will become apparent once we get into derivatives, okay, it can be really handy to have your exponential functions in terms of e instead of whatever base they are currently in. Okay, again, we'll see that in a couple lessons, but base e makes it really easy to take derivatives. Okay. So here's something. We got f of x equals 3 to the power 3 times 2 to the power of x. Okay, I'm going to rewrite my function in terms of base e. So on the side, okay, I would like to replace 2 with some power of e. So I'm going to say e to the power of k is equal to 2. Now I need to solve that for k. So I'm going to take my log on both sides. All right, so the k comes down. Oops, I didn't take log on that side. Okay, so k is equal to ln of 2. So now I go back into my original expression, 3 times, okay, and I replace 2 with e to the power of k, which I just figured out, e ln 2 times x. Okay, last but not least, to tie this up a little bit, I use my power to a power law, so I can multiply these two exponents together. So this means it's 3 times e to the power of x times ln 2. Okay, and now I've changed my function from base 2 to base e. Okay, you can do this with any power if you want. It's the same process. Okay, so we're going to do one more here. Okay, here's 1,000 times 1/3 to the power of x over 2. So again, I start with e to the k is equal to 1/3. Okay, so a little trick here with the fraction exponents, okay, is we're going to rewrite the fraction because I have 1 over something. Okay, I'm going to rewrite it. This is equal to 3 to the power of -1. Okay, this way I don't end up with the fraction 1/3 inside my exponent on top of the other fraction that's already there. Okay, so I take the ln on both sides. Okay, so now I can bring down the power on both sides. K comes down on the left, and on the right, the -1 comes outside. So I have negative ln 3. Whoops, get that off there. And then I divide both sides. So I don't have to divide anything. Ln e becomes 1. So k is equal to negative ln 3. Okay, now I go back into my function. Okay, and I replace the 1/3 with e to the power of negative ln 3. Okay, and again, I tidy up my exponent. So this becomes 1,000 e to the power of negative x ln 3 over 2. Okay, and I've rewritten my function in terms of e. Okay, so those are the basics of how to use e and ln, the natural logarithm. So there's the practice work I would like you to have a look at. And of course, if you have questions about it, please send me a message.